Hey guys, my name is Spencer Templeton. I am a physics graduate student from the University of Missouri in St. Louis, and I'm going to be presenting on Galileo Galilei and his contributions to optics. Hope you enjoy it. I'm going to start off with a brief biography of Galileo. He's a pretty big household name. I'm sure you've heard of him before, so hopefully you'll learn a thing or two that maybe you didn't know before this presentation. We'll start with his early life and education. He was born in 1564 in Pisa, Italy. That's just a little bit west of Florence. So this is right near the heartland of the Italian Renaissance. So definitely surrounded by a lot of knowledgeable people and lots of science and innovation going on then. He did some private tutoring, or about the age of 10. This was pretty typical for somebody who's coming from a well-off family, not like they had a whole lot going for public education. And shortly after that, he went to monastery. He actually, while he was there, he went to the very famous Vallombrosa Abbey, which is still in existence today, just outside of Florence. And he actually really fell in love with the hermit lifestyle. He really wanted to actually join up there at the monastery, but his father really pressured him to basically go to med school. And so a few years later, he enrolls at the University of Pisa. You can see the kind of famous Pisa Tower there, Leaning Pisa Tower. And he initially starts with the medical degree that his father wanted him to get. But his real interest lied with mathematics. He just loved mathematics. And so after a few years of being at the university, he took some geometry classes, studying Euclid's methods and elements, and eventually he decided to just drop out of medical school altogether. That is really where he begins his true professional career. He actually starts teaching in Siena, again, really close to Florence, heartland of the Renaissance. And within a year of doing that teaching job, he decides to go back to Vallombrosa, lands a job there. And while he's teaching at the abbey that he actually did his monasterial school at, he writes a publication called The Little Balance. Now, this is not something that he's well known for. This is one of the most important things that he ever did academically. He invented or improved upon a hydrostatic balance. This is a modern replica you can see in the picture that basically helps jewelers measure precious metals. And in doing this and writing his little treatise on it, he impressed some very important people, including Christopher Clavius. And so that reputation building right there really catapulted his career. And a few years later, he actually was able to become the chair of mathematics at the University of Pisa, which was a much bigger deal than just teaching in Siena or at Vallombrosa. A few years later, he lands a really nice gig actually at the University of Padua. Again, he's really built up his reputation with that relationship with Christopher Clavius, and he's become this big expert on specific gravities and finding the center of mass of different shapes. For 18 years, he'd be there, and while he's there, he eventually gets a letter from a friend, Paolo Sarpi, talking about this spyglass. This is actually the very device developed by Lippershey that you may have seen in the previous presentation for this course. And so in May of 1609, Galileo actually decides to try and create a telescope himself. And he does. He makes one. He doesn't really have a whole lot of information from Lippershey's design, but he creates one that has about 3 to 4 magnification on it, which is not too shabby. And shortly after that, just a few months later, he's actually made a better version that's about 8 to 10 times better. And he actually demonstrates this to the Venetian Senate. This is a really big deal. In this time period, the going thoughts with the spyglass was that it'd be useful for military and naval warfare. Venetian Navy is a really huge presence in the Mediterranean. They're looking for every edge against the Ottomans. And so they decide that they will actually give him sole rights to produce this for a lot of money. Now, this is kind of a sham because the telescope really was not a secret, but the Venetian Senate didn't know that at the time. So Galileo made a lot of money off of this. And this really began a habit of him self-promoting himself to really build up his brand and to land a lot of lucrative jobs and other similar gigs in the future. Shortly after he's improved his telescope, he eventually does get a version that's about 20-ish magnitude. And very quickly, he makes several just astronomically important discoveries. In November of that same year, he actually looks at the moon and he notices the moon has lunar craters and mountains. It's not this perfect sphere. A month after that, he starts exploring the Milky Way, which at the time just looked like this milky stream or band, and he actually notices their individual stars. And shortly after that, he famously discovers the moons around Jupiter, which is really one of the biggest changing things in the scientific revolution at the time. He's really starting to become famous now. In March 1610, he publishes his first truly major work, Starry Messenger. This includes all his observations up to this point. So we're talking about the moons of Jupiter, the fact that the moon has mountains and craters, is not a perfect sphere, the fact that the Milky Way is individual stars. This actually makes him a pretty big celebrity in northern Italy. And not just to, make the money and get some fame, Galileo actually decides to name the Jovian moons the Medicean stars. This is to honor Cosimo de' Medici, very famous family historically that time in Italy. And this guy is actually the Duke of Tuscany, which would oversee Florence. So he's already trying to ingratiate himself with some big, powerful, influential people. And a few months after that, the Grand Duke responds. He got a really nice, pretty telescope from Galileo. And so he decides to honor Galileo. Galileo is able to resign from his position at Padua. He had been there for 18 years, and he's actually able to get this basically honorary title of chief mathematician for the University of Pisa. And he's technically in name this private mathematician and natural philosopher actually for this Grand Duke. So he's making a lot of money, and he's basically free to do whatever he wants. He doesn't really have any teaching responsibilities with this. It's just a really good gig for him. There's a lot of other events going on where he's building connections throughout this time. In 1609, he's accepted into the Lycean Academy. This is kind of a elite club of the who's who's for those interested in making observations in outer space with telescopes and refined spyglasses. And a couple years after that, he gets this nice banquet at the Roman College. He's meeting up with a lot of famous people in Rome. So he's really starting to build a reputation, making a lot of connections, and starting to become a big shot in the scientific community. With that, we're going to start looking at actually the specifics of this telescope that made him so famous and successful. So we're going to look at the Galilean telescope. This is a picture right here of one of two that still exist. So we're going to look at the physics behind it. His original refracting design has two lenses inside a very thin tube body, as you can see in that previous picture. The objective lens, which faces whatever you're looking at, he originally used a plano-convex lens. Lots of Galilean models today actually use truly convex lens. They're curved on both sides, but he used one that was flat on one side because it's a lot easier to make with primitive tools. That lens converges the light, and then the other side, you have an eyepiece. It's a plano-concave lens. Again, most telescopes today that are Galilean design, they actually are curved on both sides, but again, it's easier to make it with primitive tools if one side's flat. And this lens diverges the light, so you can see the light comes in the objective, it gets converged, and then it gets split up again so that it goes back to being parallel when it enters your eye. One of the advantages of this telescope is that it creates an upright image. You have to appreciate the historical basis for these early spyglasses, is that they were primarily thought of being useful for things like military warfare, naval usage in the Mediterranean. So they weren't really expecting, this to only be used in outer space. So the fact that it was upright was a really big deal. And that's why he personally did not pursue designs that would compromise that for possible other benefits. The magnification power grew significantly. His first one, about 3 or 4 magnitude. It makes things a little bit bigger, useful on Earth, but not so much useful for seeing things in space. Eventually, though, his best one is estimated to have a magnification of somewhere around 30 times, which is pretty good and allowed him to make some of the biggest discoveries in the history of humanity when it comes to outer space. So here's another picture of 2 original telescopes he made. These are the only 2 that are still around. All the others are basically replicas that have been very meticulously handcrafted to mimic those. These 2 are currently held at the Institute and Museum of the History of Science in Florence, Italy. And if you put that in Italian, the acronym there is IMSS, which is going to come up in a moment. The historical dimensions and properties are not particularly locked down. We do have these 2 replicas, but because they're so fragile, you're not even allowed to touch them anymore. So if you want to actually measure them, you basically have to take a picture of them and infer how long they are, how wide they are. We don't even really have good numbers on the actual lenses. We have an objective lens from one of those telescopes, and we have an eyepiece lens from the other. So we don't even have 2 lenses from the same telescope. What we do know, based off the specs and sort of his own writings, is that the original images that he would have been seeing were probably a little blurry and distorted. and also his field of view based on his design was quite small. So there were some limitations on what he could do, but he still was able to make some big discoveries. Here's a better picture of the two being on display. The IMSS, that's the name of the place holding them, and then they name these things INV for inventories 2,427. So this one is a wooden tube. It's not really exciting or interesting looking, but this was an actual one used for field research. It had an optical power of about 14, and it's a little over a meter long, somewhere around 120 centimeters or so. The bottom one, inventory number 2428, this one was actually made to look really pretty. So even though the optical power is only marginally better, it's got really pretty gold leaves on it. It was originally made with red leather. It's kind of browned a bit over time. It's really sturdy. Those wooden staves are mixed with resin to give it lots of strength. This was a kind of telescope that someone like Galileo would give to a friend that's maybe really powerful and rich to sort of ingratiate himself with them and move himself up the social ladder. Now that we've kind of talked about the physics behind his telescope, we're going to actually talk about his specific discoveries in astronomy, because those were some of the biggest contributions he made using his optical instruments. So here's a brief timeline of the major things that he discovered. In 1609, as we mentioned earlier, he was finding the mountains and craters on the moon. Before telescopes, people actually had this idea that the moon was a perfect sphere, so he's kind of disrupting that. He also noticed that the Milky Way is actually individual stars. And really just more in general, he's able to see stars that you can't even see with the naked eye. Next year, makes a big discovery that he's known for, discovering the 4 big moons around Jupiter. Sometimes they're referred to as the Galilean moons in honor of him. A couple months after that, he's actually discovering Saturn's rings. We're going to talk about that in a moment, but I put that in quotes because he didn't actually realize they were rings at the time. And a few months after that, he's just seeing the phases of Venus. And a couple years later, he continues his work with an even better telescope. That's where he's really getting to that 30 times magnification. And he actually sees Neptune as well as sunspots. So these are his biggest things in astronomy. We're going to look at each of these in greater detail. Talking about the surface of the moon, so in November 1609, on November 30th, he first started recording his observations of the moon. You can see in these drawings that he's showing the moon is really textured. It has some roughness to it. It's not this perfect sphere. This is a really big deal, because showing that the moon is not perfectly spherical starts to disrupt one of Aristotle's theories about the celestial heavens, where everything in the heavens was a perfect sphere. And that was kind of the ruling, prevailing theory for well over a millennia. So this is really big news. He also discovers the moons of Jupiter. On January 7th of 1610, he discovers what he, in his own words, said were 3 fixed stars. You could barely see them, but they were near Jupiter. And a few days later, he noticed that one of them had actually disappeared. Now he could only see 2. And he started to realize, when he just eventually discovered a 4th one that just kind of came out of nowhere, that these were not fixed objects. They were definitely moving. And he concluded, and it turns out correctly, because one of them would disappear and then they'd come back and they were moving side to side, that they were actually orbiting Jupiter. And so this is a really big deal, because now he's able to get some good data. By 1612, just 2 years later, he actually has measured their periods. So he's got solid proof that these things are actually orbiting Jupiter. This is a huge deal, because this is the first time of solid proof that something in the heavens for sure does not orbit the Earth. And that really begs the question then, if the moons of Jupiter are orbiting Jupiter rather than the Earth, what other things are also not orbiting the Earth? He also looks at Saturn. Now, this picture on the left is a modern image. You can tell by the simple fact that it's colored. But if you had a blurry telescope, a not very good one, you would see something like this. And this is probably pretty close to what Galileo saw. So the things on left and right are, we know that they're rings, but he would have just seen those as blurry orbs. And so he thought Saturn was actually a triple system of something. And so he actually drew a picture describing what he saw. He thought that there were 3 orbs. He got a little confused, though, because every once in a while when we look at Saturn, you actually see it on edge, so to speak, where the rings are completely flat relative to the Earth, and then they just disappear. So suddenly these 2 orbs on the side just disappeared, and he really didn't understand what that was, because he didn't have a telescope good enough to make out those rings. He also recognized that Venus actually has phases. So in September of that same year, he put his scope on Venus, and he noticed that Venus goes not just through phases, but a full set of phases, just like our moon does. And he concluded that this is only possible if you have either Venus going around the sun and the Earth going around the sun, or Venus goes around the sun and then the sun orbits the Earth. It doesn't really prove one versus the other, but it definitely disproves the idea that everything revolves around the Earth. This is just simply not possible in a traditional geocentric model. If Venus and the sun both orbited the Earth, there would be no way you'd be able to see the phases. So this is a picture of our solar system. You can kind of see the relative position of Earth to Venus, giving you each of the phases. And if you can imagine Venus and the sun going around the Earth, there's absolutely no way you'd be able to see all of the phases. You'd either be able to see one half of the phases or the other, depending on whether Venus or the sun was closer to Earth. But there's no way you'd be able to see both. So this is a really big deal. Combined with the moons of Jupiter, he's now really starting to tear down that geocentric model. This is not absolute proof that everything goes around the sun, but it's definitely proof that not everything can go around the Earth. And that's a huge transformation in the minds of a lot of intellectuals. He also notices sunspots a couple years later, and when he's doing some extra explorations, 1612 to 1613. Now, he's not stupid. He doesn't just straight up look at the sun. He would project it on paper, and then he would basically draw a sketch of what he saw. And what he noticed, and I'm going to play this short video, what he noticed is that he would look at these sunspots the same time of day every day for a period of a month, and he would see that the sunspots would move. They would sort of ish maintain a shape, so he could tell which sunspot was which, but they definitely were moving. This is another huge deal. This is similar to showing that the moon has mountains and craters on it. He's really tearing down that Aristotelian view that the universe is filled with all these perfect heavenly bodies and everything's a perfect sphere and everything moves in perfect circles. The fact that the sun now has sunspots which move and change over time really starts tearing that down. So we've kind of looked at the optics of his telescope. We've started to look at the observations he's made. So let's really focus on the legacy. What did he leave behind with all of these observations and all of this technology? Well, shortly after all of this success and fame, he incidentally writes a letter to a Grand Duchess, famous royalty. This was sort of a friend of a friend that was curious as to whether Copernicus's idea of a heliocentric universe was correct or not. And in that letter, Galileo explicitly supported heliocentrism. He did not do this necessarily on purpose. He wasn't trying to make a stance. He just inadvertently said that. And unfortunately, this letter, now it's in writing, and a lot of his opponents began circulating this. Now, nothing really came of it at the time, but a year or so later, independent of Galileo's own views, a lot of other people were starting to consider Copernicus's idea of a heliocentric model, where the sun, and rather than the Earth, is at the center of the universe. And so this inquisition by the Catholic Church basically explicitly condemned this model. And Galileo, because of what he wrote in this letter, was told, you cannot consider these beliefs, you cannot spread them anymore. That was not a problem for him in public for quite some time. But 16 or so years later, he wrote one of his biggest works, Dialogue Concerning the Two Chief World Systems, which from now on we'll just refer to as his dialogue. And basically, he has two characters in there argue against each other, one in favor of Copernicus's heliocentrism and one against it. And he inadvertently, in doing this, he basically makes fun of the Pope. He did not intend to do that, but he does. And the Pope at this time is also under a lot of political pressure because there's a lot of people within the church hierarchy that really do not want Copernicus's philosophy to take root. And so basically, for political reasons, Galileo is actually put on trial for heresy. And it takes a while for the trial to occur. He's in really poor health, so he can't even make it to Rome on time. And so a year later, he is actually found guilty, and he is sentenced to prison. Now, I put that in quotes because it turns out they really just put him in house arrest. But still, that's a pretty strong message. And he also was told that his most recent work, Dialogue, and all his future works, they would be banned. They'd not be allowed to be published. He actually had to get publications made in Florence. He couldn't publish in Rome anymore because of this incident, which is usually referred to now as the Galileo affair. So that was basically the end of the major contributions in his life. Because after that, the combination of not being allowed to publish and his poor health and losing some of his family members, he really lost a lot of his productivity. So he died on January 8th at the ripe old age of 77, had a fever and some heart conditions. And because of being labeled as a heretic, he was originally buried at a no-name place. And it took almost a century before things smoothed over and he was actually given a proper tomb at the Basilica of Santa Croce in Florence, Italy, which is basically where his family was from. So kind of a synopsis of his lasting legacy here. He made obviously some contributions to optics, but the real thing is not so much his design. Honestly, his design is really not that impressive. In fact, right around the same time, Kepler made a design that had much better magnification and had a much bigger field of view. But because Galileo was able to document all these amazing discoveries, he really inspired a lot of people to start using the telescope. Remember, he was making a name for himself. He was making a lot of money with these cush jobs, writing lots of publications that are getting widely circulated. And so a lot of people, such as Kepler, took that as a cue, maybe this is a good way to get in the game as well. He also documented a use of a compound microscope, and it seems like that's the first use of one. So he basically took his practice with making telescopes and sort of turned it around to see the really, really small. He actually used that compound microscope to look at insects, and that inspired obviously a whole field of biology and things smaller than what the naked eye can see. Of course, in astronomy, that's where his biggest discoveries made an impact on humanity and how science has progressed. A lot of his discoveries challenged the geocentric model where the Earth is at the center. As some examples, the lunar surface and the sunspots, they basically upended this idea set forth by Aristotle that everything in the heavens is these perfect celestial spheres that go in perfect circles and they're perfectly smooth and they're made of this perfect quintessent substance. He's really sort of smashed through that idea. And this doesn't prove anything right, but it does make people start to question the status quo. The moons of Jupiter do a similar thing. It definitely is very, very convincing evidence that not everything revolves around the Earth. And if the moons of Jupiter don't go around the Earth, that opens a door to consider other things perhaps not revolving around the Earth. And the phases of Venus, that was a huge deal because while it doesn't prove everything goes around the sun, it definitely proves not everything can go around the Earth. There's just no way for that to be possible if both the Venus and the sun are orbiting the Earth. And then, of course, in science in general, because he was using evidence, empirical evidence, to support the heliocentric model and to challenge the geocentric one, he really gave a good name to the scientific method and the idea of using evidence as opposed to your gut or intuition or tradition. And so while he had a lot of wrong theories, one of the nice things about Galileo is that he was in many cases willing to retract or change his beliefs as contradictory evidence came through. And that's not something that you see with a lot of scientists. And so that part of his legacy and really making the scientific method validated, I think is probably one of his biggest things, even though it's not specific to any one science. I hope you enjoyed my presentation on Galileo Galilei. Here's my bibliography. Mainly I used MacTutor and Wikipedia to get some facts, but I also used a couple other sources as well. Thank you for your time.